All right. Okay, so like I said, today we'll be working on looking at the structures of coordination complexes. And you had a few minutes to try to fill in the first chart where we're looking at our different shapes for our transition metals. We'll compare the coordination numbers, right? We want to also look at the shape and the angles when we look at our respective coordination complexes. So for our first molecule, we can see that we have 6 different ligands attached to our metal center. So this would give us a coordination number of 6, right? And the shape here was octahedral. This is our most common shape. And the angle here will be 90 degrees. Next, we have our trigonal bipyramidal shape. And for our trigonal bipyramidal shape, we have a coordination number of 5. And the angles between our ligands here will be 90 degrees and 120 degrees. We can also get our square pyramidal shape, which also has a coordination of 5. And for our square pyramidal shape, all of our ligands are 90 degrees apart. Next, we have our square planar coordination complex, and this has a coordination number of 4. And then all of our angles here are also 90 degrees. And then we'll have another 4 coordination number metal complex. This would be our tetrahedral species. And the coordination number here is 109.5 degrees. And then we can have our trigonal planar species, which has a coordination of 3. So this is trigonal planar. And all of the angles between those ligands are 120 degrees apart. And then we also have a linear species with a coordination number of 2. So this is linear. And we can see that our 2 ligands are 180 degrees apart, right? So those are the general structures of our coordination complexes with coordination number, shape, and angles. Now let's talk about geometric isomers. So we can have square planar geometric isomers, where we have, for geometric isomers, if we have 2 of the same type of ligand, we can consider it to be cis or trans. And for our cis ligand, we're saying that if we have a square planar species, if we have 2 identical ligands A and 2 identical ligands B, we can say that our ligands A are 90 degrees apart, and our ligands B are also 90 degrees apart. And then for our trans species, we're saying that our ligands A and B are 180 degrees apart, right? They're 180 degrees away from one another. So that would be our trans species. So that's if we have 2 for our square planar geometric isomer, if we have 2 of each type of ligand. If we have 3 of one type of ligand and 1 of the other, there's only 1 possible isomer. So in this case, now we can have 1 B species, and then we have 3 A's ligands, and then this would just be 1 isomer, only 1 isomer, right? So that's our square planar geometric isomer. We can also have octahedral geometric isomers, and we'll have 2 different types of octahedral geometric isomers. One will be our cis, or let's actually put trans first. So one will be our trans versus our cis isomer, and the other is our facial versus our meridional isomer, right? So facial, fac, meridional, mer. And for our trans isomer, we're saying that our identical ligand, so now we have 2 ligands that are identical. In this case, it's our ligand B. Those will be 180 degrees away from each other like they were in our trans square planar complex, right? So we can put our B ligands 180 degrees away from each other. And then the other 4 ligands we have are all ligand A, so we can put those in our other positions. And we'll call the positions above and below the plane of the metal our axial positions. So these are axial. And if we are in the equator of our axial, if we're in the equator of our metal, we'll call all 4 of these positions, let's highlight them, 1, 2, 3, 4. These would be our equatorial positions. So we'll put our axial positions in yellow and our equatorial positions in green, right? So those are the two positions we can have. And when two identical ligands are 180 degrees away from each other in our axial position, we'll call that trans. And if they are 90 degrees away from each other, we'll call that cis. So if we put our Bs 90 degrees away from each other, and then our A's and all the other sites, this would now be our cis isomer, right? So once again, you can see that our B ligands are now in a different arrangement. So that's one pair of geometric isomers we can have for an octahedral complex. The other pair of geometrical isomers we can have for an octahedral complex is spatial or meridional. And the difference that we see here is whether we have 2 of the same type of ligand or 3 of the same type of ligand. If we have 3 of the same type of ligand, then we'll have to use the facial and meridional designation, right? So if we're saying that it's facial, what we're saying is that all of the B ligands are on the same, have the same angle arrangement. So all of our ligands B should be 90 degrees apart. And since we have 3 A's, our ligands A will also be 90 degrees apart. For our meridional species, we should have 2 of our B ligands that are 180 degrees apart, and then 1 pair that is 90 degrees apart. And then we'll replace all the other sites with ligand A, right? So that's facial versus meridional, and those are our geometric isomers. If we want to go to our optical isomers, now things get a little bit more difficult, right? So now we'll take a species where we have 2 of each type of ligand. So we have 2 A's, B's, and C's. And for our optical isomers, we want to incorporate all of these species. So let's pick a few colors. So let's say that we have ligand A, and we'll put them 90 degrees away from each other. We'll also put ligand B 90 degrees away from each other, and then we'll decide to put ligand C 90 degrees away from each other, right? So that's one pair. Another way that we can do it, if we want to make it identical, is we can put B's 90 degrees away from each other here, right? So there and there. Our A's can be 90 degrees away from each other here and here, and our C's can be, I want to put different colors. Our A's can be 90 degrees away from each other here and here, and our C's would be 90 degrees away from each other here and here. And with these 2 molecules, it may be a little bit difficult to see, but these are actually identical compounds, right? So these are identical. And that's because if we were to rotate one of these molecules, it will completely line up with the other. So if you can imagine, if we were to rotate this B to the front, right? So if we were to rotate this B to the front, then everything gets shifted by 90 degrees. And this allows us to move C, B to the back, and then our 2 A's kind of switch positions. So those will be identical. Another way that we can get a pair of identical drawings is if we include our atoms for our ligands for B there, right? We can say that we have A here, and then our C ligands can go there. And then we can also say that we have A here, our B's would go here and here, and then our C ligands would go here and here. So this is another pair of identical. This is another pair of identical species. And when we compare the molecule on the left and the right, so if we just choose one of these molecules, right, this molecule with this molecule, you'll notice that they're mirror images of each other. And if we can get a mirror plane in between our molecule, we'll call these enantiomers. So these are actually enantiomers. And that just means that they are non-superimposable mirror images. Right? So those are our enantiomers. So now, even though we've drawn 4 structures, right? And technically we've only drawn 2 isomers because they're identical. So 4 structures, but only 2 isomers so far. So this is isomer 1, and this is isomer 2. We can eliminate this isomer and this isomer because they're identical. And now we want to think about ways that we can draw additional isomers. So the way that we can do that is, now what we want to do, you'll notice that in our trend, we have our identical B ligands, cis here. They're cis here. They're cis in this position, and then they're also cis in this position. So if we want to draw more isomers, what we can do now is we can actually change the location of our B ligands and make them trans to one another, right? So if we take B and make them trans to one another, then we can decide where we want to put our C and A ligands, and we can decide to put, we just want to be methodical. So if we want to put our A ligands on the same side, we can put them there, and then we can put C on the opposite side, right? So that would be another isomer. And then if we want to draw a different set of isomers, so this is where we have our B isomers trans to one another. We can have another option where our B isomers are cis to one another. So we can put our B isomers there. And then this allows us to put our C isomers in the opposite position, and now our A ligands will be trans, right? So this will be another isomer. So let's see if these are identical. And we can see that these should not be identical because now we have our, I'll put it in yellow, right? Before we have our ligands B in the equatorial position in one isomer. And then the other isomer, our ligands B are in the axial position. So there's no way that we can change the degree between these two species. So in our in the second example, in this isomer, our ligands B are 90 degrees apart, and in this isomer, they're 180 degrees apart. So these are actually distinct isomers. So now we've identified isomer 3 and isomer 4, right? So let's see if we can draw any more isomers. So now what we can do is we've made, you'll notice that we made B trans, we've made A trans, right? You can imagine that it's also possible to make C trans. So let's make our C ligands trans, and then we'll put our A and B ligands in the cis positions, right? So we'll say that our B is cis and our A ligands are cis, and that will be a distinctly different isomer because in the other two isomers, we saw that our C ligand was cis here and cis here, right? And now they're trans in this one. So this will be a different isomer. And we should be able to get one more isomer, right? So now we can say that we have one pair of trans isomers. But what if we decided to have two pairs of trans isomers, right? So what if we make both our B and our C? What if we make all of our isomers trans, our ligands trans? So if we make B trans, and we make A trans, and we make C trans, then now, once again, we've generated a complex where we can't get these angles to change, right? So now everything's 180 degrees apart. So we've actually generated a fifth and sixth isomer, right? So these would be our different isomers possible for this one formula, Ma2B2C2. And the way that another methodical way that you can think about doing it is picking just one pair of your, if you do have an identical ligand, picking that pair and keeping that pair consistent, and then moving your other ligands. So you'll notice that what I did here was I had my B ligands in cis positions, right? And you saw that that occurred basically 1, 2, 3 times. And then I had an option, 4 times. And then I had an option where my B ligands were trans, and that occurred twice, right? So I pick one pair of ligands that are identical, if I can pick one of my geometric isomers, and make all of the different kind of deviations from that one pair of geometric isomers. It's easier to find the isomers. So we have a total of 6 isomers here. Right? So that's for an octahedral complex. What if we have a tetrahedral complex? For our tetrahedral complex, things get a little bit easier because if we have a metal center M and we have 4 different ligands, we can write them anywhere, A, B, C, and D. If we want to draw the mirror image, right, we'd have A there, B here, C there, and D there. And since we have one metal center with 4 different substituents, these would be enantiomers as well, because they're non-superimposable mirror images. We can also see enantiomers with bidentate ligands. So one common bidentate ligand that we've seen already is our ethylene diamine, which is abbreviated EN. And if you want to think about this as having an enantiomer, right, we can draw our EN ligands, our bidentate ligand there, here, and here. And then if we want to think about drawing a mirror image of sorts, right, we can get an EN here, a pair here, and then our last enamine, diethylamine species here. So another way that I like to think of it, for our bidentate ligand,